Yes, so welcome everyone, and thank you very much for the invitation again. It's my great pleasure to be here today. So my goal today is essentially to justify the previous lecture that was given here on the zero number of delay differential equations with negative feedback. So if you remember, we had some delay differential equation, f of xt minus 1. And this came together with, this was scalar. So f is a function from R2 to R as regular as we need. And this came together with a monotone feedback assumption, negative feedback assumption. I believe it was called A1 in the lecture notes. One second. Yes, A1. So this negative feedback condition was that y f of 0y was negative whenever y was non-zero, right? There were further assumptions on the structure, on the derivatives of f at 0, but we will not be using those today. And the main goal of today is, well, there was this function v defined on real functions, defined on the whole real line, and it gave us back an integer. And the idea was that if you take a function, the value v of x was given by, well, there is this function here, and then there is 0 here. Find the smallest 0 after going forward in time, and then call it sigma, then take sigma minus 1, and count the number of sign changes of the function on this interval, and this was the value v. So this is sort of the definition of the function, but I'm not giving it precisely. And now my question for today is, what's v good for? So the whole goal today will be to justify the introduction of this function v and to showcase an example of what can be done with it. And hopefully by the end of the day, I will convince you that v provides enough information to describe the whole set of periodic solutions of certain delay differential equations. So I'm going to move to a slightly different setting from this that we had here. Maybe we can call this equation 1, and this assumption was A1. And instead, I'm going to consider delay differential equations of the form x dot t equals g of xt minus 1. And here I call it g to make it clear that this is different from 1. And for these equations, I'm going to assume something slightly different from A1, rather A1 star. And A1 star is that the derivative with respect to this second component, so here again, g from R2 to R, let us not worry too much about regularity. And the derivative with respect to this second component of g will always be negative. My claim is that v is good for describing periodic solutions of 2. So g and f are slightly different, but they both sort of have this delayed negative feedback theme to them, right? So this assumption A1 star here is called A1 star because it's very similar to A1. And I will show in a moment how they are connected. But let me give you an idea of what applications could come out of this, or some examples of systems of this type. So there is, for example, what you call the shower equation, I believe, in the course, right? So shower equation, which is very simple, right? It's even linear. So I think that the notation you used was T dot, because it's the temperature of the water when you're in the shower, right? And now there is some temperature. I've introduced some additional coefficients that minus k, yes. There is a certain coefficient k, and here you have temperature, but at a different time, right? And this delay comes given by the length of the pipe, right? Essentially, so the temperature of the water coming out of the pipes is essentially produced by your heater, maybe, I don't know, 5 seconds ago, and now you decide to change it a little bit, and maybe it's too hot. But you will only notice 5 seconds later, right? Yeah. And yeah, maybe if this coefficient is too large, eventually you will just boil yourself to death. But the thing is that you want to reach a certain desired temperature, right? And then small values of k are fine because eventually you reach your stable shower temperature, your pleasant temperature. But very large values of k can more or less kill you. But this equation is not very interesting in the sense that it's linear, and scalar linear delay equations can be solved by Laplace transform. So we sort of have an idea of how to solve this guy. We shouldn't use V for looking for periodic solutions of this equation. Rather, we should solve a linear equation, a certain characteristic equation. There are further examples in the literature, though. There is an ENSO model by Schopf and Suarez. So ENSO stands for El Niño Southern Oscillation Phenomenon. So this is a periodic weather oscillation happening in the Pacific, right? And these guys claimed that these oscillations could be generated by traveling waves of warm water in oceanic currents. And they proposed a model for this. So again, this is T prime is now the temperature of the water, is something like this, cube minus a parameter alpha, and then there is a delay. So this delay is essentially it's correlated to the traveling time of these oceanic currents happening in the Pacific. And you have a nonlinear instantaneous reaction to changes in the water temperature. So this is slightly more complicated, but it's still depending on linearly on the delay. So yes, essentially the delay here appears as the water hits. Yes, I never really understood this very well. Yes, essentially the delay appears as an interaction between hot water and cold water in the sort of middle of the Pacific. And essentially the temperature of the water is being affected by how much it hit it in the previous season, because as it hits the coast, as a water wave hits the coast and cools down, it comes back and sort of cools the water in the middle of the ocean.
So then the delay is very large, right?
Yes, the delay is very large in the regime of months, I think. Yes. And further examples, and maybe the most famous one, is the Hutchinson equation, also known as Wright's equation.
Oh, it's called delay logistic equation.
You call it delay logistic equation. So the delay logistic equation.
After coordinate transformation, change of coordinate.
So let me stick to the notation of T, even though now we are not modeling temperatures anymore. We are now modeling, in the case of Hutchinson, population of rodents. And this is the instantaneous temperature multiplying 1 minus temperature delay. So somehow this was supposed to model the interaction between a population of newborn rodents and the old rodents, essentially. So there is like a fixed delay, which stands for the maturation time of the population of rodents. And yes, if you think of the instantaneous population as one species and the delayed population as a different species, y of t, then this looks very much like Lotka-Volterra, except that this is not a closed equation, right? And now somebody may come up with a very straightforward question, which is, well, do they actually satisfy A1 star? So I think we all agree that as long as I pick alpha positive here or k positive there, these two will satisfy the A1 star assumption, right? But how about the Hutchinson equation? Is that also the case?
No, this is in my whole assignment.
Is it?
There's a transformation to make it.
But it only works for positive solutions.
Okay.
Okay. So here, because this is a biological system, people in biology are always interested in positive solutions. And the reason is that you cannot expect to have a negative population, right? So in biology, we want X positive, right? And then we do, there is a certain change, exponential of something, right? And I will not do it here because then I will mess it up. But essentially, yes, this equation, at least for positive solutions, is equivalent to an equation of this type, right? Minus tau minus 1. And now this went back into the monotone feedback, right? Okay, so far so good. We have examples. All of them fit the motive of somehow processing an input, right? And here there is a certain control, and it produces an output. And then the feedback, there is a feedback loop, right? There is a certain delay here, which may be induced by, say, the maturation time of the rodent population, or say by the traveling time of the waves in the current, or by the length of the pipe, wherever you live in your apartment complex. And this is fed back into the control. So you always want to sort of bring your system back to a state that's somehow desirable. This could be applied to many other systems. Like, for example, say that you want to drive straight and then your car is sort of going to the left or going to the right, and you want to turn it right again, turn it left again. It also appears widely in self-inhibitory systems. Say in the mammalian vertebration clock, you can always find phenomena such as this. And people have actually tried to model these more complicated systems using a similar ansatz that you somehow have a negative feedback. But how does this equation, how do these equations connect to what we were doing last week, is the question. So let me erase this very quickly. I hope it's fine. I mean, this is just to set up the stage. Well, the key is not to study this equation, is not to study 2, but rather to compare solutions of 2 using 1. So our approach today, or the idea, is to compare solutions of 2 using 1, and the zero number, and v. Okay, and how do we do that? Well, notice the following. Let me take 2 different solutions of 2. And please stop me anytime if I'm too fast, or if there are any questions. Say that x1t and x2t are solutions of 2. Then write y of t equals x1 t minus x2 of t. I claim y dot of t is actually of the form a of t y of t plus bt y of t minus 1. Is everybody happy with this? I claim it. I will prove in a moment. Where b of t is but a real function and it's strictly negative. So all of a sudden this looks a little bit more like f of yt, comma, yt minus 1. Okay, this looks a lot like 1, but I'm missing something, right? What am I missing? T. So when I want to compare solutions of 2, I obtain a slightly different version of 1 with t. Lucky us, the zero number v still works on solutions of this type. So there was this theorem, I think in the LaTeX file it was called theorem 0, but I don't remember the number. Theorem 171 in the notes. Lucky us, or fortunately for us, the zero number v preserves most of its properties, even if f is time dependent. That is the most important property of this function is not that it's autonomous, but rather that you have this product being negative all of the time. So as long as this holds with a t here, and let's say that it holds uniformly for being safe, well, it holds in a Lipschitz sense or something. As long as I have something like this, then the zero number still exists and retains its properties from theorem 171. That is, the zero number v of xt is still, of y, is a non-increasing function for the y of t solving 1. This was 1. This is 2. Yeah? This is 3, right? Yes. And 4. 4 was that v y t is constant in t implies all zeros are simple. This result is not from the same paper as the original proof of the zero number that was given last week, but rather was done a few months later, I believe, by some guy called Lin Zhao in 1989, I think. So as we will see, the most important properties of this v function is the fact that it's a non-increasing function of time. So it's a Lyapunov function, but with discrete values. And that it drops strictly, provided that we have double zeros or multiple zeros. So you see, this condition 4, the fact that this condition 4 tells you if v is a constant along a function, then all the zeros of that function are simple. But what's actually interesting is the negation of 4. So if not all of the zeros are simple, then it means that the zero number must be different when you go back in time than from when you go forward in time. There must be some drop, because it cannot be a constant, right? Since it's not a constant, then in the past it must be a larger value than in the future. So this is a strict dropping condition. This tells you double zeros imply a dropping in the zero number.
But it doesn't specify when in T there's a drop.
No.
Yeah, that's different.
No. And these are the two properties that we will use most in the follow. Okay, so where was I? Yes. So first of all, how do we show that actually that x1t and x2t actually solve something of this type? Any ideas? I mean, I don't know if people check the lecture notes before the lecture or not.
They are not supposed to do that.
Okay, they don't have to, right? Okay, and because this looks a little bit mysterious, right? I just jumped from taking two different solutions to saying that the difference of solutions solves a linear equation. Well, what's the right choice for a of t and b of t? It turns out that you can do this explicitly. And unless I messed up, which I may have, at is actually integral from 0 to 1, derivative in the first component of f, and now theta x1t, 1 minus theta x2t, x1 t minus 1.
Maybe partial 1 G.
Yes, it's g. Actually, I also have to correct the lecture notes. Yes, this is also a typo in the notes. And it's not partial 1, right? It's this is partial 1. The next one is partial 2. This is also wrong, right? So
I never tell my student that the next one is guaranteed to be L33.
oh, and they are not.
Never.
Partial 2g.
I can guarantee you otherwise.
T minus 1.
So this is by fundamental set of calculus.
Yes, proof fundamental theorem of calculus.
Whole assignment. But this is a very useful trick, okay?
Yes, and here I'm integrating in theta. Yes. So essentially, I take this dummy variable here, and I use it to construct these coefficients by integration of this dummy variable. And now it's clear that b must be negative, because it's just the integral of evaluating this derivative in the second component. And we assumed that the derivative in the second component was negative all along, right? Yes. So good, so far so good.
So let me make a remark here.
Yes.
So be careful here, the x1 and x2, they are solution to nonlinear equation.
Yes.
But the difference satisfied.
Yes. So in this way, we can compare different solutions of this equation by using the zero number. Moreover, there is another aspect in which this zero number shows up in nonlinear equations, and it's again when considering linear equations in this setting. Say that I have, for example, an equilibrium or a periodic solution. I think that if you want to check this in the script, this is what they call C1. So case 1 of application of this equation 1 to nonlinear equations of type 2.